Good. So welcome to my second slide. This one will be on others and multiplexers. In this slide, we're going to explore the fundamental digital circuit that forms the backbone of modern computers, as multiplexers and others. We are going to understand their critical rules and how they enable complex digital systems. So what is a multiplexer? A multiplexer is a crucial digital circuit designed to select one of several input signals and forward the selected inputs into a single output line. Now think of it as a data selector. Based on a set of select lines, it determines which input pathway is active. Common examples include the 2 to 1, 4 to 1, and 8 to 1 multiplexers, each distinguished by the number of inputs they can handle. So the types of multiplexers include, just as I said before, so the 2 to 1 multiplexer features two data inputs and one single select line, which allows the choice between two distinct input signals. And the 4 to 1 MUX comprises four data inputs and two select lines, enabling selection from four different data streams. And the 8 to 1 MUX also is equipped with 8 data inputs and 3 select lines, providing the capability to choose from 8 input sources. Now, multiplexer logic and implementation is also important. So the output via of a multiplexer is determined by a combination of the selected inputs using and or logic gates. For instance, in a 2 to 1 multiplexer, the output is defined by the Boolean expression just as displayed there, where D0 and D1 are the data inputs and S is the selected line. So this fundamental logic allows multiplexers to be incredibly versatile. So they can implement complex Boolean functions by appropriately setting their inputs, making them indispensable in data routing, communication systems, and general function generation within digital circuits. So what at all is an adder? We've been talking about it from the start. So an adder is a core digital circuit that performs the fundamental operations of adding binary numbers. It takes in two or more binary digits and produces two outputs, a sum bit and a carry bit. Adders are the basic building blocks of arithmetic logic units found in the CPU, enabling all arithmetic computations. The simplest type are the half adder and the full adder, which will be further explained in the next slide. So the half adder adds two single binary bits and produces a sum and a carry out bits. The full adder adds three bits, binary bits, plus two input bits and a carry in bit to produce a sum and a carry out bits. We have also ripple carry adder, a multi-bit adder constructed by chaining multiple full adders where the carry out of one stage feeds into the carry in of the next. We also have lastly the carry selector adder. Now this is a faster adder design that uses parallel computation to predict carry bits, significantly reducing propagation delays. So building adders using multiplexers. A powerful application of multiplexers is they are used in implementation or implementing complex combination circuits, such as adders. A full adder, for example, can be efficiently constructed using a 4 to 1 multiplexer. By leveraging the truth table of the sum and carry outputs, the inputs of the multiplexer are carefully chosen to select the correct sum and carry bits based on the other's input values. So this approach demonstrates the flexibility and modularity that multiplexers brings to digital logic design, allowing for compact and adaptability in the circuit's implementations. So in summary, what we've learned is a multiplexer acts as a data selector, routing one of many inputs to a single output based on control lines. Then we learned about others being performing, being things that perform binary addition, outputting sum and carrying out bits, and essential for arithmetic operations in digital systems. Then we also talked about synergy. Multiplexers can be ingeniously used to implement adders, showcasing fundamental components for building advanced digital systems and computing architecture. So thank you. This ends the slide. And